All right, folks, in the interest of time, let's get started. For those of you who don't know me, I'm Dinesh Jairaman. I'm an assistant professor here at GRASP. I work in robot learning, and today it is an honor to be able to introduce Jan Peters. Finally, actually, because we've actually been trying to bring Jan now for about a year. And I remember in spring when Antonio and I were teaching the robot learning seminar, which I think some of you were in, you might have remembered that we advertised very excitedly that Jan was visiting because it was literally that same week that we were discussing, just coincidentally, some of Jan's work. And so we were very excited, and unfortunately, Jan had to postpone them. But it turns out that actually this week in my machine learning class, we also were discussing Jan's work. So it's testament, again, coincidentally, it's testament to the fact that Jan has done so much impressive foundational work that it's kind of hard not to keep bringing him up in my classes. And so it's really a privilege to have you here. Jan is a full professor of intelligent autonomous systems at TU Darmstadt and department head at the German Research Center for AI. His dissertation was at USC, advised by Stefan Schall, and it was recognized with the Dick Voel's Best US PhD Thesis Runner-Up Award, as well as many other awards since then. Jan has really been one of the figures in the field that has produced, I think, since the early 2010s, some of the most impressive demonstrations of robot learning, including a celebrated series of work on robot table tennis and many other kind of sports-playing robots. But also a lot of foundational work on things like policy gradient algorithms for robotics, natural actor critic algorithms, and probabilistic motor primitives, and more. And more recently, Jan has also been doing really creative, very interesting work on Lagrangian neural networks, on how to introduce robotic-specific biases into the design of modern generative models like diffusion models. And I'm sure that we'll hear more about that in the talk today. If you have questions during the talk, I request that you raise your hand, and I'll try and bring my microphone over because this will be recorded and put on the YouTube channel, which also reminds me, all of the talks in this seminar series are on the YouTube channel, so you can also find past recordings there. With that, please join me once again in welcoming Jan, and Jan, take it away whenever you're ready.
All right. Thank you for that kind introduction, Dinesh. Now, with so many nice words, you have set me up for failure. But let me try to nevertheless do a good job here. So I'll be talking today about inductive biases for robot learning. And as I did my PhD 8 miles from Hollywood, let me start with a movie. This year is actually the oldest robot commercial ever. At the time, the company Unitree was so cocky that they said, let's directly put a robot into people's home. You'll see in a moment that, I'm sorry, but I don't know what is happening with it's showing on my screen. There is a cable, but this is a, can we just switch it back just maybe?
Yeah, do you have an HDMI?
No, I don't. Let's quickly, no, that doesn't help.
I think Siri is getting technical help.
Well, that's a bad start.
It's interesting that it was completely okay up until the moment you started presenting. It's back.
It's back. Let's give it.
Yeah. All right. Great. Yeah.
Okay. Let's hope that it stays back. So this movie is so fascinating because it is so wonderfully anachronistic, right? On the one hand, you have the robot doing exactly what every other coral paper does these days, right? Moving some cutlery around. On the other hand, you have the housewife staying at home, the guy going in a suit to work at a admin job in the bank, and the robot is supposed to be the future mate. And of course, all of us know, despite that this was completely programmed, it was completely staged. Every single object was perfectly placed. There were desired trajectories. And if one thing had been done slightly differently, it would have completely failed. But on the other hand, it is not so. And today we could take our average high school students give them our tools of today and they could hack it up very cheaply. Back then, you needed to have had to have at least a master's degree to pull this off just because of programming. But under the hood, it's actually not so different from the way most of industry, for example, uses robots. Now, let me fast forward to the end. That glass of champagne from the robot is practically, of course, not the case. And the big question is, why don't we have such robots? And maybe the question should be a different one. The question should be, where have robots been successful? Coming to you from Germany, a country which just is dissolving its car industry, but we would have lost it for sure 50 years ago if we hadn't been so good at industrial robotics, where, of course, the whole environment was done at 150 micrometers, perfectly placed. And as a robot, as I've worked for 2 years as an engineer here for industry, also in robotics, and I can tell you, all the people there told us back then, we don't want to see sensors. If you have a sensor, something is wrong. So clearly not about the environment. We all know that a lawnmower typically follows a wire in the grass. And anybody who's ever bought a Roomba knows the first thing you do when you have a Roomba is you rearrange your furniture so that it doesn't get stuck. So in other words, we have typically adapted the tasks to the robots, and we should instead have adapted the robots to the tasks. So why is that? Well, obviously, much of that came through the fact that when we started robotics, we had very little computation, we had very little data. Learning was frowned upon even in many areas. So when I told my first advisor at DLR during my undergrad, I wanted to do learning for robotics, he said, no, don't do it. You'll never be successful, you'll never get a job, and nobody will ever be interested in your work. So that was, of course, the analytical robotics age. And in many ways, of course, the analytical robotics age was super powerful, right? Accurate forward models, meaning physics simulators, are fantastic. They're great prior. Physical principles give us great simulators. And even if our models are typically wrong, they are also often useful, or at least some of them. And finally, unmodeled nonlinearities, though, and all the things which come with a bad model are, well, kind of problematic. The next challenge, of course, was planning, due to the which also, again, in the analytical robotics age was at the core, but it comes with an exponential explosion of states, and replanning is hard. And if you're using a bad model, you have significant optimization biases, which can be highly problematic. And finally, well, there was always the hope that fast feedback control could act as an error killer. Instead, it had made industrial robotics build robots which were easy to control with classical methods, meaning they were stiff and power hungry. So clearly, this was not suited to start out with for adaptation. Now, in today's world, I don't need to persuade anybody that we should do robot learning. Again, that was very, very different during my PhD still. And we typically, after seeing all the successes from OpenAI over the DeepMind, and that we know that learning actually can accomplish a lot. And by now we have gone too far to the opposite extreme. At last IROS, I overheard a student making a statement in a talk saying, oh, there was no robot learning before transformers. That should shock everyone. So these are just the outtakes from around 2009 to 2013 from my team, where we have tasks like imitation learning, combined with for the small pattern imitation learning combined with the reinforcement learning for, yes? Oh, Russell Anderson was here in the grass lab. Russell Anderson was here in the grass lab. Russell Anderson was here in the grass lab? Yes. Oh, I didn't know that. But I thought he got his PhD from MIT. Okay.
He had to build a special computer in order to make things move fast enough so that it can play, but yes.
Yes. And I think the vision chip alone cost $2 million in 1980 dollars, right? That would be like 20 millions today, right? So
Sometimes.
yes. But Russell built his work on analytical robotics. These here were done by learning, all with reinforcement learning and imitation learning.
So they know this is one of the things we should be proud of.
Yes, absolutely. I'm very aware of what kind of a pioneering lab institute I'm here. Yeah. So yeah, these were 4 examples from my lab where learning worked already, well, 15 years ago, or 10 to 15 years ago. Now, since then, of course, the black box big data learning age has happened. And on the one hand, it's something which many people predicted for a very long time, right? I mean, I talked to Jürgen long before he became, how to put this, the most obnoxious person at telling everybody that he invented everything first. But he really did talk about all of these things. Thanks already 15 years ago that he said, well, a highly flexible representation with the suitable algorithms is easier to train. And of course, he's right. We can learn anything with such a representation. Just unfortunately for us robotics people, also something really terrible, we can actually learn a physically implausible solution. And if we then have a small error, well, we know learning algorithms exploit errors. And well, in this case, we can have a huge optimization bias. And finally, well, black box solutions should never make us happy because they give us no insight into our solutions. Then there is the point about loads of data. And we all, as roboticists, know robots live in real time. This idea of Silicon Valley that they can just hire all the master students we can ever produce, give them giant salaries, put them into exoskeleton-like suits, and make them teleoperate enough humanoids is never going to produce the data which we are going to need, right? So instead, we need to see that in, like, let's say, robot table tennis, you get a lot of data per second, but it's actually only very few trajectories which matter. And we have this crazy part of having so much useless data in a very fast state action stream, but actually not a lot of useful data. And then, well, in the real world, we'd have real damages. And well, when you start telling these things to a machine learning person, they'll just tell you, oh, physics simulators, we should use them as data generators. We should ignore real robots. But then we're back to the age which analytical robotics couldn't solve. And if we have good enough physics simulators that we can do everything by simulation, well, analytical robotics alone should actually be enough. And finally, the question of computation is not the same for us as for somebody who deals with a static data set, right? We cannot do what OpenAI did for the Rubik's Cube of having the power of 2 nuclear power stations for so that they could pay for the power of their compute. So instead, we would actually like to have it that our robots have the power consumption of a human brain, which is 20 watts, and can be handled on board in real time. And I have as little communication as possible because communication will be flawed. So quite clearly, we have severe limitations if we are just doing the black box blind brute force approach. So in other words, what do we need? We need really a chimera of both eras. And how do we get there best? Well, this is, ignore this, I don't know why that's what. My best guess is that we should do this using the right robotics inductive biases. So what is an inductive bias? Here's my favorite definition. An inductive bias allows a learning algorithm to prioritize one solution or interpretation over another, independent of the observed data. Inductive biases can express assumptions about either the data generating process or the space of solutions. And I think as community, our goal really has to be to ask the questions of what inductive biases does robotics offer? And how can we use them to improve robot learning and especially robot reinforcement learning as the more active component? Therefore, the remainder of my talk has a rather straightforward outline. I will be talking about a few of the inductive biases that I have found helpful. So let's start with the bon mot. When I told Stefan Schall during in my PhD in the first year, I wanted to do robot reinforcement learning, he said like, oh my God, Jan, don't do it. Michael Jordan has just told me he has written the best letters for all of his guys and they all didn't get faculty jobs. Do imitation learning. It is always easier to do imitation learning than reinforcement learning. And as we see from what's currently happening in Silicon Valley, we have gone full circle. We are right back to imitation learning and behavioral cloning, precisely where we were in, well, 20 years ago. So reinforcement learning is the harder problem, and imitation learning is always easier than reinforcement learning. And if you look at the cost function behind it, I'm sorry, the black on blue doesn't really look that good. If you look on the cost function behind it, it is basically just the KL between the state distribution you're generating times the policy and your data set. So it's one of the most straightforward problems to minimize from a machine learning point of view. And again, the first algorithms are super old. You actually can go to the early 1960s, like 61, 62, 63. You find work by Michie and Chambers and a lot of other people at Edinburgh. In the 90s, you find all the work by Claude Semmet to show all the cleanup effects of that the chestnut trained by behavioral cloning can actually be better than the teacher, just because regularization takes the tremor of the teacher out of the data. So it is, of course, super powerful. But at the same time, we also know that behavioral cloning has a trouble of data imbalances, which can best be treated by introducing additional assumptions, for example, by having constraints on the propagation of distributions. If you put both of these together, you are actually with the model-based behavioral cloning, which in fact wasn't even covered in the reinforcement learning community properly until basically the 2010s. One of the nicest papers is the one by Peter Englert, shown here. The dual problem got a lot of attention thanks to Brian Siebert, Abdeslam Boularias, and especially, of course, Peter Abil and Andrew Ng. But it actually turns out that this dual problem, well, you can make this dual problem work for a lot of different physics scenarios, then it can be very powerful. But in the general sense, the dual problem here is actually harder than model-based behavioral cloning. So one tiny takeaway, don't ever do inverse reinforcement learning. Really focus on model-based behavioral cloning, because in inverse reinforcement learning, you have quadratically many constraints in the general solution and linearly many optimization terms. And it's exactly the opposite for model-based behavioral cloning. So you're fundamentally going to have an easier optimization problem. Now, if you look at reinforcement learning, it's much more annoying, right? The cost function of reinforcement learning has no notion of data in there. If you add the assumptions to model-based behavioral cloning, you have the same thing. And if you look at the dual problem for the value function, or if you decode the whole problem by introducing Bellman's principle of optimality, in all of these cases, you have no natural notion of data. And in fact, this bogged reinforcement learning down for a very, very long time, since there were only heuristic ways of introducing data into the update process, is by so-called averagers in the 90s and 2010s, or by staying so close to the data that you could always do something like, for example, a policy gradient update. However, if you use my first inductive bias, that you should always regularize all your updates towards your training data, you will automatically end up with a combination of imitation and reinforcement learning. Here, for example, introduced as a constraint, which we called relative entropy policy search, and which is in fact the generalization of many things, including natural policy gradients, natural actor critic, TRPO, SAC, mellow-max and soft-max solutions, or other entropy regularization. And it is still surprisingly the best algorithm when you're trying to learn, or the best framework when you're trying to learn highly dynamic tasks. So here we have a task which was initially done by a master's student. So this was his master's thesis, and he showed me he can learn to juggle two balls with one arm with this algorithm really well. with just 400 rollouts or, well, 56 minutes of robot experience. The sentence down there with the 30 minutes is wrong. He can actually do 3 hours. Then the robot overheats and we have to turn it off. And this worked out of the box. That's pretty much, this worked after them. At the end of Gnosis, this is out of the box, so you could really get everyone to the lab and show them anytime they wanted how the whole learning process would work, pretty much deterministically. And so being an evil advisor, I told him, yeah, you know, you're defending your master's thesis next week, but I want to see 2 arms juggle together. 1 arm is not enough. I just wanted to make, I don't know, I just had a bad day and wanted to make his life a bit hell. He called, this was on Friday, I told him this, and on Monday he called me to the lab and he showed me this. And he said, Jan, I did the 2 arms, but you know, I made my life actually more difficult by using them together. I could have just trained 2 arms to do the 2-ball behavior in separate, and then I would have had 4 balls. I would have just done the same behavior twice in parallel. Here he created a completely new behavior. I hired him, of course, for a PhD. Right now, he is at 5 balls, which for this kind of setup for a learned solution is still the world record. And he can do 7 balls. Just after about 2 or 3 minutes, the robot makes a very annoying noise. So we are all a bit worried about going on. But I've already started to make his life hell again. I've told him the physical limit is 17 balls, so that should be a good PhD requirement. Whether we have special purpose hardware. No, these are just buried WAMs, but these are buried WAMs, but they're the high speed modification, the high voltage modification. They're fast enough, and especially they can do the accelerations which we need. It would still be nice if they were, I don't know, carbon instead of metal, since anytime you're still juggling with the two kilogram masses at the end effectors in the end, which is still or at the elbow, 2 kilograms. So that's still way too much from my perspective, but that's a different story. So first inductive bias, the next 2 inductive biases are coupled. And now there is an old bon mot in robot learning that, well, models can be powerful, but errors in models are often exploited by reinforcement learning algorithms. I learned this the very hard way. So when I graduated with my PhD and I initially wanted to stay in the US for a postdoc, go the faculty career and so on, then a Max Planck director came to me and said, like, Jan, I can give you loads of money, skip this whole postdoc stuff and come to me, and all you have to do is impress me. In Germany, you have this weird system of Max Planck where one guy is so powerful as a king, he can hand out money. But if you're on his bad side, it's not a fun place to be. So I wanted to impress him. And obviously, the first thing you want to do when you impress somebody is fastly have an impressive demo. So I took a model-based reinforcement learning algorithm, trained it on first in simulation, worked beautifully. Then I trained it on the real robot. I compared the models of the real robot, and it all looked beautifully. The solution looked, again, beautiful on the simulator and on the model. And I thought, like, okay, great. I'll run it on the robot. What happened? It made. So really bad start for me. I had to go to my director and tell him, please, can you give me another 20K to repair my robot? Not a good start, but it taught me one lesson which all of you should never forget. When you're learning a model, even accuracy can mean very little. This model was more accurate than any model which you could get from physics. But a machine learning algorithm, of course, has one important inductive bias, which in this case worked against us. That's the inductive bias of smoothness. So it smoothed out some of the stuff which shouldn't have been smooth. And with the result, it was super accurate on the data, but it was not physically consistent. And again, the reinforcement learning algorithm is also very smart. It directly figured out, oh, here I get free energy. With the free energy, I can do everything. You kind of feel like the German government. And voila, you have the shot of, well, creating a solution which looks really great, but on a real robot will actually create instability and loads of props. So that was a painful lesson back then, but it also gave us very, very great research topics, as most painful lessons do. That's what all good advisors know. When students fail, then typically great things happen next. When students always succeed, they're sometimes extremely boring. So for me, the key lesson was that we need to focus what's between the extremes. On the one extreme, we have what many people do today. We just want to learn black boxes. On the other extreme, we have what we classically did in a good engineering education. We create fantastic models by hand. We put in the CAD data. We make it as good as we can. We take the robot apart. We do everything we can do to get the classical model well. And what happens? Well, the classical model is never good enough, and the black box model is always going to be dangerous. From the model-based perspective, there are, of course, ways of like going towards system identification, where you do some data-driven steps, but you also end up in system identification with non-convex optimization problems, which can give you solutions which can destroy your robot. And they're actually more frequent because of the lump parameter, the processes in there, which, again, I could tell you many stories about. But we learned, actually, that learning can be used much more effectively if we're trying to learn physics-compatible solutions. And two of such approaches were the differentiable Newton-Euler algorithms and the deep Lagrangian neural networks. You have to put in differently many assumptions, like, let's say, rigid body dynamics in the first case, in the second case, just that it's Lagrangian mechanics. And you can learn forward models, inverse models, and even energy models, which can be very powerful to give you special control solutions. Now, let me tell you what we mean, for example, by Lagrangian neural networks. Lagrangian neural networks, we have black box layers as in order to represent something which can only become kinetic energy. We have another black box layers which give you potential energy where there is less constraints in there. And we impose upon the laws then of Lagrangian mechanics and conservation of energy. And then just add the right kind of cost terms of predicting torques well, and also of having energy conservation the right way in there. And voila, we actually get surprisingly good model learning approaches. So here you see, again, a ball in the cup scenario, where in this case, we used 4 minutes of motor babbling. If just from 4 minutes of motor babbling, you can actually learn a ball in the cup with a higher repeatability by just wiggling your robot around, and at the same time even get a transferability to different string lengths, which works out of the box. And if you use the concept of energy and use the concept of energy in there, you can actually learn things like with this little Pareto pendulum or the card pole also out of the box by just learning the model and then using energy-based control to swing it up. Interestingly, system identification fails for the Pareto pendulum due to the tiny size and the bad relation between sensing and eigenvalues of the system. System identification fails completely if you don't really, really strongly smoothen out the data or do something where you really know the solution already. My current students, so this was a few years back, but my current students actually figured out then how to deal with the fact that we have unmodeled linearities and higher order dynamics in nearly every system. Like in the buried WEM, we have typically just motor side control, and it doesn't really behave like a rigid body system anymore. So we have to clearly deal with this fact and still stay physically consistent. And well, in order to do that, you can actually make sure that you learn additional states from histories by just having an LSTM in there. And one thing which I find the coolest, which is still unpublished, is that if you bring in more knowledge, like a very, very little known decomposition of the inertia metrics for the floating base systems, you can actually have this advantage of having the sparsity in the floating base systems. There are many empty components being zero. You can learn a very sparse inertia metrics, which then allows you to learn loads of good dynamics models of floating base systems. So this is really ongoing work right now. And it works across all of these robots. I've just imposed the rule now in my lab that everything has to work on at least 2 humanoids and 2 quadrupeds. So we are already at 3 quadrupeds, but only 1 humanoid here. Since we need one which can do torque sensing here, and for that we are going to borrow one from DLR. And it's, well, for that, it's showing already really, really good results. This sparse inertia metrics actually allows Lagrangian algorithms to be more data efficient and require less parameters than a Newton-Euler based approach, which was really counterintuitive from all of our original upbringing, from textbooks always saying, well, for an arm, Newton-Euler is always preferable. So this gives us our second inductive bias. Well, whatever model you train in robotics, you need to ensure that a physically consistent model is being learned. Now, that's unfortunately not all which is wrong about simulation and training in simulations. The second thing which is wrong is even crazier. We call it the simulation optimization bias. It is basically the fact that the true optimal solution is guaranteed to be underestimated by an optimal solution on a limited number of physics worlds, a limited number of samples, a limited number of trials, of episodes, whatever quantity you would like to act upon. And it even is intuitively totally clear why this happens. This graph makes it very nicely plausible, where there is a mean function, and in this case, just a constant covariance, that whatever function you fit is likely to have a maximum at a very different location. So with other words, when we're training in simulation, we are guaranteed to be wrong. So what do we need to do? Well, we need to quantify this simulation optimization bias whenever we do training and simulation, and then subsequently make sure that we create the right number of worlds so that we can minimize this bias. My student first took the most trivial example he could think of, the control engineering 101 example of a ball on a plate, and then he did very evil things to the solution. He took the ball apart and he filled it with the sand, paper clips, hydraulic oil, which was a real mess, and many other things. And he could show that you can learn solutions which generalize nicely if you have quantified your simulation optimization bias. And similar things you can do if you do evil things to your card pole, and also again quantify your simulation optimization bias. So this gives us the third inductive bias. Generally, always try to control your optimization biases when you're training with models or simulation, or even with just samples from the real system. Back to our outline, let's go for our fourth inductive bias, and let's start again with the bon mot. Now, I'm sure you're telling your students the same as what I'm telling mine. You're not a real roboticist if you haven't broken your robot. Since obviously that's part of being a roboticist. But the fastest way to break your robot is if you allow a learning algorithm to do exploration. The first person I could find who had ever done reinforcement learning for legged locomotion was a guy called Winfried Ilg. He never succeeded, but he tried very hard. And he was famous in his lab because, well, every time he went to the lab, the robot was broken afterwards by exploration. And I think is really the key lesson. Well, we need to find exploration always which is safe when you want to train on real systems. And now it's again time to talk to the classical roboticists. The classical roboticist will tell you one thing which all reinforcement learning people are typically doing wrong. When you let's say you open your favorite OpenAI gym, or your favorite sample problems from DeepMind, and you look into the reward functions, you see that they are pages long, and they include terms on, oh, don't hit into the table too far, or things where you think like, okay, they should not be in the reward function, even intuitively. Well, then you have hit exactly the point, and that classical robotics problems typically hide these difficulties not in the reward function, but in the constraints. And that gives us our fourth inductive bias, since we should use our constraints to direct our exploration. So for us, this gave us a method called exploration on the constraint manifold, where we construct a constraint manifold for which we have many ways of doing that. For example, if you are interacting directly in contact with the environment, you could first have the robot do motor babbling in low gain mode, and you would nicely acquire, well, what are the constraints, or others you could probably better do by hand, like maximum torques or certain torque force relationships. Others, again, you can demonstrate by imitation learning quite effectively. But no matter how you obtain it, it's important to obtain this constraint manifold and then determine the basis of this manifold and subsequently ensure that all your actions are taken always in the null space of this constraint manifold, all your explorations, and that you never violate the constraint manifold. One problem where we tried this out is where we've shown that this is very successful is robot air hockey, where we've even run competitions over the last couple of years between teams from 15 different universities. And some of these solutions are clearly just at its student level. Other ones you can see that it has done really complicated things like this dynamic hitting task, for example. So that gave us our fifth inductive bias. Let's use our constraints to direct our exploration. And well, then we are really in the modern world and we should stop ignoring foundation models. And everybody tells everyone these days foundation models will take over robotics. And in robotics, everybody who has a longer term background knows this can't be the case. But we are not really, we're not really leading the discussion yet onto the, I think, right, right parcours from my perspective. And obviously we tried just like everybody else. We took, you can take a data set of nice discrete movements, like from the robot air hockey scenario. You can give it a lingual description of hitting a puck into the goal fast and a goal image. And then you can take pi0, octo, whatever one you like. And even after a lot of post-training on the data set, you will have things like that it will hit the table, that it will have complete garbage when you're just moving the puck a little bit to a region it hasn't seen. And you see what I think everyone else always sees again and again, that it's not so straightforward. And here, we need to really make sure to use the right restrictive inductive biases in order to limit the solution generation and ensure that it's always projected onto a safe policy manifold. No, let me skip this. So for air hockey, it is actually enough to just create inductive biases based on the CAT data. And you already get, if you project the whole policy into the right space, you end up getting decent movement. And in this case, even sim2real works out of the box. So this gives us our fifth inductive bias. We need, when we want to make really, really large models, really work over more general policies, we need to bring in policy class restrictions, and these need to consider both kinematic and dynamic constraints. Let's go for our seventh inductive bias. And well, it makes me really sad sometimes these days to see talks in conferences, especially at Coral, because you see the robot doing this here. And you feel like, okay, this is not how good robotics should look like, right? Smooth movement is something anybody who had a classical robotics education knows is the single first thing you should ensure with your solution. And in addition to that, when you then go to the robots of most people and you push the robot up by the arm, you recognize they're in high gain mode. The robot is super stiff. Again, the biggest lesson of all the people like Neville Hogan who looked into biomechanics of that robots should be not stiff, that they should be compliant and low gain is increasingly forgotten. That is bad. Good control is being ignored in the learning age. In fact, many people don't use the feed-forward term at all and then have just this very stiff gain matrix in there. And the lack of smoothness and too high gains are significant problems if we want robots to leave the labs. So what should we do instead? Well, we need to have smooth trajectories, both the feed-forward term of giving us feed-forward torque so that the control law can stay silent, as well as to have low gain control matrices which depend on both the position, velocity, and typically even the stage of the trajectory. Now, for many classical robotics people and people who've been around for longer times, like our pioneers, this is a very natural thing to say. If you say this at choral, people will sometimes ask you, what is a gain? But that's a different story. But what is really cool is if you really then learn policies with lower gains, you can see, so here my student takes just a tissue to push our G1 around, and in low gain control, learned low gain control, it can actually nicely cope with this. Or you can put it on a skateboard and wibble it around, and it will do many of the natural steps without having an analytical model here. Where here in this case, this box, if you were in a high gain mode, you would, it's one of these very shaky plastic boxes, it would directly break. And in fact, if you train systems to fulfill smooth movement and low gain with the right cost terms, you can get a lot more performance. This is the H1 we have with this trained with the same method, and it gets 60% more robust and 40% more energy efficient. And luckily also a hell of a lot safer. We did all of the experiments in our park around our institute, and that is unfortunately full of drunken homeless people who come to hug our robot. And with the feet, we're still scared as hell, but at least we know the arms won't kill due to the low gain control. And therefore, well, use proper control, punish torque changes, punish high gains, punish high accelerations is really, really crucial when you want to learn good solutions. So this brings me to my 7th inductive bias. And well, I don't know about you, but when I learned how to play tennis, there was this blonde, long-haired guy who would just say, oh, move like this and go with the flow. And in the first 300 trials, I hated him and thought, like, what the heck is this guy saying? Same for skiing. Oh, these are just muggles. Let your body go down, go with the flow. And again, hated the guy, but after a few days of doing it, wow, it's actually easy. And I think there's an important lesson in there. And the lesson is we don't plan a perfect trajectory. We don't invert mechanics or do any of the things many people propose we humans do in the past. We much rather have a body which enables us to do learning very well. So one thing which we did is we decided, let's build a robot, and let's build a robot purely for performance, not for anything else, and bring in the most important concepts. So we want to have high accelerations, therefore strong actuators, small moving masses, and we want to have an antagonistic setup so that the robot can hit into the walls and not break itself, but also that it is naturally, typically in a compliant state, unless you do co-contraction on purpose. And well, we built this, and really we built it for performance and learning, but not for control. So wiggling around, we could show crazily cool things. And then we showed it to the control engineers, and there was a very, very famous guy from MIT who came to visit us, and he said, like, this may be a computer scientist's dream, but it's a control engineer's nightmare. He was, of course, totally right. So it was supposed to be that. Now, what we ended up doing is we could directly use it with reinforcement learning, in this case, starting with motor babbling, so really just wiggling around, we could walk out of the lab and come back 14 hours later, and it could play table tennis like this and return balls like this. And the key lesson here is, well, we allowed our learning algorithm to simply excite the natural robot dynamics and let the natural robot dynamics guide the robot through the learning process. And I think that's also a really important inductive bias. So that brings me to one last one. And again, with the bon mot, since it seemed like one of the classical critiques about learning is whenever you have a new robot, you have to learn everything again from scratch. Right? How should something transfer from a humanoid to a quadruped, from one quadruped to the other? That seemed like a fundamental limit to learning. and actually a really good argument against learning and pro-analytical robotics. Now, my student Nico Bollinger, he challenged this, and he basically said, well, why shouldn't we train across many embodiments? In order to do that, he created body encodings where he would have one big vector where many locations, where the different locations, different kinds of joints would be put in, like a front hip of a quadruped, a left shoulder, and which always have both an observation and a description of the joint. And the description could look like this, so it has all the stuff we know about the robot. And at the same time, the observation would be position, velocity, and maybe even the previous action. If he puts this all together, he gets one of these beautiful neural network diagrams we all have in our papers these days, with the joint encoders, joint descriptions all in there, then a deep architecture. And the amazing part then is he can train he can train across many different robots, and obviously test also on robots which it had seen, like the one up here, as well as robots that it hadn't seen. So this robot, which you see down here, has 1 degree of freedom typically not found in quadrupeds. It has a spinal cord. And anybody who has compared a real dog to a quadruped knows that a real dog barely goes out of the singularities. It's mainly straight legs, so that it doesn't need so much energy, doesn't do the bending of the knees all the time. And it can only do that because the spinal cord allows it to shift more of the mass. Now, obviously, this is a rather imperfect spinal cord, but it uses it actually all the time, especially for going on under obstacles. And in fact, he can train by now on 50 base robots, real and simulated. And with embodiment randomization and all kinds of other changes to the robot, he gets a data set of 10 million robots and even managed to do, zero-shot transfer to new robots like the one you've seen on the previous slide. So, with other words, the right embodiment encoding can actually enable generalization across bodies. With that, I'm at my conclusion. Here are some inductive biases, and thank you for your attention. And if you want to read some of the papers, they're all here one more time. And thank you for your attention.
Thank you, Jan, for the really wonderful series of vignettes and wisdom. And while the audience are beginning to come up with questions, I thought I could kickstart. There was a thing that you said about kind of controlling the simulation optimization bias, and I wonder if I could kind of double click on that a little bit. It sounded kind of magical that we're somehow able to get over this problem that your optimizer is somehow going to hack your model and all of its kind of potential weaknesses. And so how is it, could you give us some insight on how it is that one might actually control this gap?
Okay, so maybe it's overstating to say that I can get rid of the problem, but I can quantify it. I can actually statistically quantify how big the optimization bias should be based on relatively mild assumptions and the fact that we have data. Yeah, and if
without knowledge of the true model?
Without knowledge of the true model.
I see.
But it can, of course, happen that it never goes down.
Yeah.
So in this case, we don't solve the problem, we are just aware of the problem. But it allows us to sometimes choose solutions where the optimization bias has gone down to so small levels that we don't think it affects the solution anymore. And that's, I think, the key reason why it helps us to quantify optimization biases.
So am I right to think that you're able to, for any solution, think about what the difference might be under small modifications to the assumed model? Like for any policy, you're able to predict the performance gaps under small. So it's almost like a robustness measure for the policy to the kind of changes in the model. Yes. Is that right?
I think that's precisely right.
That makes sense.
It's kind of like how a Puck base bound, for example, would also help you to understand based on the number of your samples, the probability assumptions, on the
Right.
problem, allows you to understand a supervised learning method better, but doesn't give you the solution, of course.
Right. So it's maybe kind of a more
Enables you to get
principled way to do
better.
something like domain randomization style training, which would
Yes.
be kind of just
The
a
domain organization
pure-
works totally in sync with that's
Right,
in fact,
right.
you can see this as a type of better controlled domain randomization.
I see, I see. Yeah, thank you. Other questions, Antonio?
Thank you, very cool talk. I have a question about inductive bias 5, the physics compatible models for
Okay.
control. So the task that you showed seem to be like one task, right? One robot, one task.
Numbering wrong. But okay.
And of course,
Maybe
like
that
your
is not
methods
you.
are general, like you could train any task, but still like one method, one task, right? And of course, like one state, one physics model. I was wondering if you have any thought on multiple tasks. So in that case, the state is not exactly well defined. Well, technically, it is the combination of all states for all tasks. The model is not exactly well defined. It's, again, you could say it's the combination of all models, but this starts to explode in complexity. I was wondering if you had any thought on this.
So, I mean, we of course here focused mainly of the problems close to our embodiment. And you're of course totally right. If we go for arbitrary tasks, we will have an open-ended state description. And it's at some point here, so it's a bit further away from what we did with inductive bias 5. But I think we have to figure out how to get more and more away from the Savage's small worlds to Savage's big worlds. So the statistician Savage in the 50s already coined this, of that our notion of state implies that we have a small world. In the moment where only in the moment where we drop the notion of state, or make state in a form open-ended, we can actually deal in the same way. But in that case, it will be also harder and harder to do more than learning heuristics that work across many problems. And I think that's, of course, a super important goal, to learn heuristics which work across many tasks. But then we're deep into, well, multitask learning from classical machine learning, and we can probably harvest from a lot of different domains there.
Other questions from the audience? Michael.
Thanks for the really nice talk and the perspective. You sort of started with this dichotomy between, big learn models, big learn methods and classical robotics. And one of the points you made was like the classical methods struggle with these things that you really can't model, right? I'm not sure. I don't know. What is your thought on like, what is the solution there, right? Because some of the things you talked about today, which are really inspiring, incorporating Lagrangian dynamics, still is not doing, the contact and the friction in the weird little, dissipative terms, as I understand it, that you can't model accurately. And then a lot of the later work was also kind of on the, sim to real side as well. So yeah, I mean, I guess for me or for any, people in the room, how are we going to approach those problems of things that are really unmodelable? Is it just real data, or is there more?
So I think that we need to always, there will always be things which give us generalization power. Like in physics models, typically bad physics model gives us actually much better generalization power. Things which are harvested closer to classical components will probably make us much stronger for generalization. And learning and data-driven components should always be closer to the things which need to either adapt fast to a situation or which help us to do a situation again that we have seen before. I think that's kind of my high-level view here to your answer. I mean, I totally agree that there is no one silver bullet to kill them all, to kill the werewolf, whatever. But this is the closest it gets.
Thank you for such nice wisdom. I have one question. So A lot of the inductive biases that you discussed are coming perhaps from a more control theoretic point of view. So how robust are these results to errors in perception is one question. And when we think of detecting objects around the environment with perception, what is your opinion or insight into inductive biases that help perception action control loops become robust? Perception has very different failure modes. No feedback is allowed or done. Control benefits from feedback, and the interaction, I think, always makes all the policies very fragile. I was curious how you think of it.
Good question. I mean, first, there's one big distinction between, so in classical, how to put this, in classical approaches from control theory, we've been too focused on the probability distributions, which we know how to handle analytically, while in perception, people were for a long time much further of dropping these notions. I mean, 15 years ago, they were using also Gaussians all over, but dropping these notions is, I think, super critical here, and to have bounds that don't rely upon these notions in the first place. Since if you take, let's say you take a ball tracking setup, you will directly see that you have loads of noise, but none of the noise looks like in a textbook. Simply because there are just jumps in there. There are things which have heavy tails and are bimodal and skewed, and typically a mixture of bimodal skewed things. And that is just things like table tennis. So I think, and that gets, of course, worse and worse the more complex the perception problem is. What I think should be, for the second question, I understand more as a, how to put this, a more long-term perspective, right? And what one for me, and I would answer it only by posing the big open question, that is, well, what is the right bottleneck between perception and action? Since we humans are very, very capable of finding the right bottleneck. Like I give you as an example, baseball, where we humans work in the end with just very, very few perception heuristics. So the outfielder in baseball, for example, focuses on the ball and tries to center it on the retina. By that, he gets automatically the angle of the ball. So it's a very, very active process here. And at the same time, using just this tiny yellow spot at the retina, it's a crazy control problem he does there too, right? Just to get the perception. Then he runs backwards, always keeping the same angle, which gives him a policy which is compatible for his motor control to the policy which does the ball tracking and ball angle tracking for him. Figuring out how to make perception also an active process so that we can limit the bandwidth between our much, much superior sensors we have in robotics, right? I mean, but we have in sensing, except for speed, for that event-based cameras, will at some point give us give us an outperformance of real-time speed. We can perceive so much more, but we need to figure out how to get this amount of data in real time to just so much data as we need, and we need to make that an active process. So apply maybe all the things we apply to robots, again, to the perception system, so that the perception system just feeds us out the data we need for the task and makes the perception system focus completely on these components. Just like the outfielder in baseball learns to first focus on the retina such that he has the ball exactly at the yellow spot, and therefore has the angle, and then just needs the heuristic of, oh, if I'm running backwards, I can nicely catch the ball. Which incidentally is a policy which makes every baseball coach mad, because they know the optimal policy is to turn around, run forward, and run and turn around again. But nobody does it.
So I
have to add one just fun thing. The only time I've ever been to a baseball game was here in Philadelphia.
So I wanted to, so I was, as I was watching your talk, I was remembering also the message that Ken Goldberg gave us actually just last week when he visited. And as you know, Ken has recently been speaking about kind of good old-fashioned engineering and its role in kind of data-driven robotics. And so, at a surface, the message was kind of similar, but I wanted to see if we could maybe pick at some of the nuanced differences. Because I think in Ken's view, it is kind of inevitable that in the end, there is going to be some big data-driven, purely data-driven approach. I mean, I'm kind of paraphrasing and might not be fully representing his view, but that's the message that I got from his presentation, that there is inevitably in the end, the method that will win will be a purely data-driven method. And we will not require inductive biases because we will have by then generated the amount of data necessary to bake those inductive biases into the parameters of the algorithm, parameters of the model, rather than manually represent and engineer those biases. And I wanted to see if I am right in understanding that you disagree with that view and whether you could make the case for that.
Okay. This is a very cool question. I'm not sure whether I understand Ken the way you understand Ken. And since I do I do think he thinks of everything as one big engineering problem, and choosing the right learning components is part of the engineering problem, and he still has some of the human engineer in mind there, and creating the right data set for all the problems we need is the way he sees it. And I think for a closed world again, like let's say we want to solve all the human tasks, we can probably pull this off, right? I mean, look at the computer vision guys. For decades, we always said we're just waiting for them doing the job, and then they had these big data sets, and suddenly they say, so when are you robotics guys doing your job, right? Things have totally turned around in robot vision. And it works because there are sufficiently many people with the cameras, there are sufficiently many robots. Lots with the cameras, we actually can have all the tasks on Earth. Now, if we look at robotics, I think the number of tasks we can generate will not stop. That's why just engineering one solution by engineering methods from both classical robotics and machine learning and engineering data sets, using these methods and then doing an iterated loop on them will never be enough. And from my side, Paul Verbis, he was one of the inventors of backpropagation 10 years before Hinton and so on. And he at some point told me in space robotics alone, they have isolated 6,000 different unsolved robotics tasks, which none of them which are treated on Earth. And that was apparently part of some NSF program in the 2010s, I think, or maybe even earlier. And so I think that is very much to the point. In an open world, we'll have open-endedly new tasks. So my perspective is that we shouldn't have the engineer predefine everything, but we should actually figure out, well, first, what inductive biases can we give the system? And then also, how can we make the system discover new inductive biases? So kind of create an automated robot engineer, just like we have created the automatic mathematics modules these days, which find occasionally new theorems with very, very little human interaction. I mean, the recent Fields medal thing didn't go to the 300 pages proof was completely automated. Just the bringing in the right intuition into it was still human done. So in the same way, I think automating the mathematician more and more is a necessity in mathematics. Automating the robotics engineer is a necessity in robotics, but we won't just converge to one solution by a mix of smart engineering and machine learning. But we really have to think of the outer loop and how the outer experimental loop could work. But I tried this as a grand proposal and I got rejected.
I have a very just high-level question. I was wondering if there are some persistent inductive biases that exist in current solutions today that you wish would go away, or you think are limiting performance, or even yeah.
Okay. Very good question. I mean, I would start right away with one of the most basic inductive bias we have in any form of supervised learning and of continuous signals. We always put in a smoothness bias, right? The smoothness bias is the reason why we cannot deal with distinction in robotics, and why we cannot deal with a lot of things which happen when it comes to contact. And if you could get rid of it, it would be wonderful. Just, I wouldn't know how to do supervised learning without at least assuming that you're piecewise smooth, which is kind of the minimal assumption for regression models, for example. So, but that's a very good question. And I think that probably, I think we as roboticists, one way I think to, especially for young PhD students who still feel they can do the things, you know, which currently few people believe in, it would be a good idea to now question all the tools we're getting from machine learning and to figure out, well, what wrong inductive biases for robotics are actually in these machine learning components. Since, again, look at the Parkinson-like robot movement you see these days. There's tons of bad biases from reinforcement learning in there. If you look at the smooth supervised learning and piecewise smooth movement, piecewise smooth functions, again, wrong. So yeah, you have a good point here. A good question. And a good way to start a PhD, to start a new topic in the PhD.
If there aren't other questions, then let us thank Jan once more for the wonderful talk. Next Friday, we have Ji Tan from Google DeepMind who'll be presenting in this series. So please come back in and let's thank Jan again.